Now let's assume that somehow we could measure all the properties of all the stars over the entire sky, and we try to essentially make sense of them all. How should we rank or organize these stars? If you paid any attention to the previous sections up to section 8, you will know how to measure a lot of these properties, and perhaps you'd have your own personal preference of how to rank stars. Perhaps you would go with just ranking them in terms of absolute magnitudes because they do not depend on a distance. Although some people may think that the perspective from the Earth provides a way to rank them. So perhaps you would use apparent magnitudes, meaning that the stars that are closer by will have lower values for those magnitudes. On top of that, we could actually use, for example, colors. We could use temperature, perhaps the strength of absorption lines. That is something we can measure in a very quantitative way. Or perhaps we could even rank stars based on the amount of heavy elements. And we can actually do spectroscopy and quantify the amount of elements which are heavier than helium, that, as we'll see, were not there to begin with when the universe began. So the important question really is, can we actually rank or classify stars in a way that is both objective and physically meaningful? Historically, perhaps one of the first and best quantitative ways to classify stars was through spectroscopy. This was done by measuring the strength of the Balmer lines. And there were really important women that perhaps are not so well known that were responsible for this system that actually still continues nowadays. They include Wilhelmina Fleming, that you can see here, and also Annie Jump Cannon, the actual author of the way that we currently rank stars, even though there were some updates in the way that we do that. From a physics perspective, if we are to rank stars in terms of the strength of the Balmer lines, then we can actually link that in terms of temperature. We've seen in section 5, and specifically section 5 part 2, if you want to check back the playlist or in the lecture notes, that is the second part of section 5. If we combine the Boltzmann equation that will tell us about excitation, essentially we want to predict the number of atoms that have electrons at n equals 2, so you can get Balmer lines versus, for example, n equals 1 in the lowest energy level, and you combine with the Saha equation that tells us about the ionization state, or the number of ionized hydrogen atoms versus neutral atoms, you can actually make a prediction of how strong Balmer lines should be. Remember that both these equations, both excitation and ionization, will depend on temperature, but the dependencies will be slightly different. One of the key predictions that we were able to do, and you can follow this in one of the questions at the end of section 5, is that even though the number of excited atoms keeps going up with temperature, the number of neutral atoms becomes increasingly smaller as you go to higher temperatures, and therefore the strength of Balmer lines will go first up with temperature, it will reach a peak, and then it will start falling down at the highest temperatures. So what does this mean if we are to rank stars in terms of the strength of the Balmer lines? Well, if we are to rank them, for example, alphabetically from A, B, C, D, and we give A to stars with the strongest Balmer lines, and therefore you expect A-class stars to have a temperature of around 9 to 10,000 Kelvin. The problem with ranking alphabetically stars in terms of the strength of the Balmer lines is that perhaps the second class that is the strongest will probably be around here, maybe call it B, but then C-class stars might be here, and then D would probably end up here, etc. And it means that if you then rank stars in terms of temperatures, you actually get a classification that no longer looks alphabetical, even though it started as something very clearly defined. In reality, the way that the system was devised was actually to get spectra for a bunch of stars, to measure the strength of the Balmer lines in absorption in an empirical way, and then to rank them from those with the highest Balmer absorption, this would be A-class stars, all the way to Q, which would have the weakest Balmer lines. Now, the modern classification did not keep all the letters from A to Q, but actually kept class A, and these are still stars which have the strongest Balmer lines, followed by B, which are stars which still have quite strong absorption lines for the Balmer lines, but not as much. And then most letters are skipped. We then have F and G, and the Sun is actually a G class star, all the way down to K, M, and O. And it turns out actually that O-class stars are actually the hottest of all main sequence stars. So almost once in a lifetime, a system in astronomy was actually logical and made sense, and due to the extraordinary efforts and work of Wilhelmina Fleming, Annie Jem Cannon, and many others. But very quickly, once we realized that physics doesn't quite track this empirical measurement, the order ended up being non-alphabetical, but the letters were kept. Most main sequence stars are therefore still currently classified using letters, but the order that we typically write them at is O, B, A, F, G, K, and M. And this is because those letters will form a sequence, essentially from the hottest to the coolest stars. But you can still remember that the letter, if you were to put them alphabetically, will give you an indication of how strong Balmer lines are for those stars. And this system was first put in place, as I told you, by Annie Jem Cannon, following the work of Antonia Maury and many others. Ultimately, and you can see how O, B, A, F, G, K, M stars would look like, they also establish a ranking in terms of color. O stars are the bluest and M-type stars are the reddest. The same thing goes for luminosity. These stars are the most luminous, they are the hottest and the largest, and as we shall see, they have the most mass, while stars on this side are the coldest, the least luminous, the smallest, and also the ones with the least mass. And it turns out that they also are the stars that actually have the longest main sequence lifetimes. In order to remember the order of these stellar classes, there's a lot of mnemonics. Perhaps the most famous one is written here, also with the colors of the stars, and it is the traditional "Oh, be a fine guy or girl and kiss me." But also there's plenty of others that people make up, including those that I made up in a few minutes before doing this, which will include overly brilliant astronomers found giant koala man, or the pre-2021 "Oh, Brexit anticipation feels good." Kidding me. This probably no longer applies, but you can still use it, and you're free to make up your own mnemonic. The most important thing is to understand that O, B, A, F, G, K, and M, they establish a sequence that is physically meaningful. And this is the reason why, even though the system started to be alphabetical in terms of Balmer lines, we've changed it so there is more physics into it. The other thing to point out is that each letter class is then actually subdivided using a numeric digit, with 0 being the hottest and 9 being the coolest, that essentially establish transitions, for example, from A to B types. You'll have, for example, a B9 followed by an A0, A1, etc., all the way down to A9 before you get to an F0 and F1. And with increasing numbers, you're going from the hottest to the coolest stars, which in color means that the color is increasing as you go from O to M, as they become redder. An important question that we need to address is exactly how do we classify stars in the modern system? And the modern system essentially has to do with the temperature. And we can use spectra to determine the spectral temperature and therefore obtain the spectral type of a star. Obviously, this means that spectroscopy is the key for spectral classification, and we can measure spectral lines, use the Boltzmann and the Saha equations, and then figure out what is the temperature. What happens, of course, is that particular absorption lines, as we can see here, can only be measured for a specific range in temperature. This is because only for this range of temperature will, for example, calcium be singly ionized. If you go to highest temperatures, then it will be doubly ionized or triply ionized. And therefore, you're looking at another line. And we've seen this in detail for hydrogen, for example, that the Balmer lines will only exist and be very strong, around 9,000 to 10,000 Kelvin. But also, it is important to understand that if you just measure the strength, say, of the Balmer lines, then there's always two solutions in temperature. And therefore, to really establish a star and its spectral type, we actually need at least two lines to break the degeneracy. For example, if we measure the line strength of hydrogen to be around here, perhaps it could be a very hot star, but if we also measure ionized calcium and it gives you a value like this, then we know that this must be the solution and not the high temperature one. In this case, a star would have a temperature of around 7,000 Kelvin. This would very likely put it in the F-class star. To be a G-class star like the Sun, then we would have to have even weaker Balmer absorption lines.